Welcome to this presentation on general linear models, moving beyond analysis of variance. My name is Chris Hand and my email address is available on this title slide. If you have any questions related to the material, please don't hesitate to contact me. One thing I would ask is that you please don't share this recording or this presentation out with the confines of the module. We'll start with an overview of this presentation. What we're going to be looking at today is a recap over what we mean when we talk about a linear model. We're going to revisit the topics of analysis of variance and regression. We want to start thinking about these as associated tests, as part of the same family. We're not going to focus hugely on regression today. That will come as part of an independent session. We're going to concentrate a lot on F statistics today and what they actually mean in terms of the logic behind them and their interpretation. We're going to talk about a lot of the assumptions and myths around analysis of variance before we then start to move beyond the analysis of variance to look at statistics and methods like the analysis of covariance and the multivariate analysis of variance. In the literature, you might hear people talking about statistical families, families of tests, and the linear model is an example of one of these families. There are a number of statistical tests that can be classified as general linear models. Generally speaking, we test the fit of our model, i.e. how well does our predicted model relate to or account for our observed data using an F statistic. And if we just pause for a moment and think where we most commonly see this F statistic in previous studies, in our previous experience of research methods, for the majority of people, it would probably have been in the context of this analysis of variance, either as a one-way analysis of variance or indeed as a multivariate analysis of variance. And the conception is that we use ANOVA to compare means, or that what an F statistic does is that it compares means across either levels of a single factor or comparing independent or interactive effects of multiple factors. Now, there is a little bit of bad practice or a misconception around this, and that would be that ANOVA and regression are very different things and that they're used for very different purposes. And if you were to ask most people who have even studied research methods and statistics to a fairly high level, what do you do with ANOVA and what do you do with regression? The majority of people would be likely to answer that you compare means with an ANOVA and you look for relationships with regressions. And what we're going to be doing in this session is trying to debunk that myth a little bit and start to try and re-establish that these techniques, these terms, are all part of the same family and they're actually much more related than we might have previously been trained to realise. Ultimately, what the F statistic does is it tests the fit of this model. So when we're looking at an analysis of variance, the model that you build is composed entirely of means. So yes, it's true in the case of an ANOVA that the F statistic is comparing means. However, that's a simplification because ultimately what all F statistics do is test the fit of a model that you have built to your observed data. And it just so happens that when we run an ANOVA, the model is only composed of means. So the ANOVA is just a special case of the general linear model. And the F statistic that is associated with an ANOVA is still ultimately the test of the fit of the linear model. Without going into the mathematics or the formulae behind the F statistic, what it ultimately represents is a ratio between systematic variance, i.e. that variance that you have introduced as a researcher or that you are attempting to quantify, versus the unsystematic variance, which is random error, individual differences, and so on. Error or variance that we have not been able to account for in our manipulation. So simplistically, this is essentially the variability due to a factor versus the variability due to error. Or alternatively, it is how much of your variance is explained by your model versus the error term. So the F statistic is also known as an F ratio because it literally examines the ratio of how much variance you can attribute to systematic factors or manipulations versus that which is due to individual differences or error. When our model's good, you should find that you have improved the prediction of the variance, i.e. you can explain a lot of the variability in your data set using either your predictors, your manipulations, and when this is the case, you should see a small difference between your model, the fit of the model, and the actual observed raw data. Mathematically, and apologise, we do have to get a little bit mathematical for a moment or two, the F statistic, the F ratio, always has to be greater than 1 to have any chance of reaching statistical significance. What this means in real terms is that your model is at least as good as no model, or the error terms. It means that they are at least equivalent, a 1-to-1 ratio. Now, one thing that you may notice in particular journals that have used APA style is that if the output of your statistical test of your linear model reveals an F ratio, an F value less than 1, you can simply report F less than 1, rather than the more typical F, degrees of freedom associated with your treatment or your factor, comma, the degrees of freedom associated with the error term, what the F value is in exact terms, the associated p-value, and perhaps a measure of effect size such as a partial eta squared. Because F, which is less than 1, can never be significant, we can to a certain extent disregard that other important information like degrees of freedom, exact p-value and effect size, because the F less than 1 can never be significant. In past studies or in past modules where research methods has been covered, we talk about assumptions of modelling or assumptions of test, and we have to be very, very careful when using linear models that we fulfill or satisfy any assumptions associated with them. And one thing that's often neglected at a practice level, if not an academic level, is the role of outliers, a subset of cases that do not fit with the general trend of the data. This is really important for allowing us to generalise our model from our sample of data to other samples and future studies, or indeed to the population that we're interested in. What is an outlier? Well, it's a case that differs substantially from the main data trend. And the problem is that a model, a general linear model, cannot accurately predict these outlying values because the model relies on the underlying trend, the majority of cases. And by definition, the outlier is outside this trend. So it is almost impossible for a good model to actually encapsulate these outlying data points. And there are a number of ways that outliers can be identified. For example, visually inspecting your data is very important, or indeed backing this up with statistical tests or quantifications of how the data could be identified as outliers. Box plots can be very useful for this, scatter plots can be very useful for this, but ultimately if you wish to quantify what is and is not considered to be an outlier, there are methods to do so. So again, at a practical level, researchers often neglect this stage of the data analysis, and it's always good practice to start off by inspecting your data, either through visual inspection or through quantification, to see if you have any outlying cases. Terms that we come across when we're dealing with outliers are unstandardized residuals, and these are the raw differences between your observed values and the values which are predicted by your model. It's essentially a measure of error. It's what's left over. It's residue in the analysis from what you've observed to what you have predicted. Now, one problem we have with unstandardized residuals is that the size of these residuals is influenced by the unit of measurement. So for instance, if we took a measure of height and we attempted to model that based on participants' weight, we might have very different unstandardized residuals if we took someone's height in centimetres as opposed to taking their height in millimetres, because the units of measurement and therefore the size of the unstandardized residuals would be much larger in the case of using millimetres. Because if we take someone's height, say 173 centimetres versus 1730 millimetres, we have by default or by the nature of our measurement introduced much more residual error using millimetres, because it's a much larger set of numbers that we're working with. There's a nice way to deal with this, and most statistical packages will do this automatically, and that's to standardize the residuals so that you withdraw or remove this artifact of response scale from the analysis. What happens with a standardized residual is that the raw differences are converted into z-scores or z-scores. This removes any issues with the underlying issues of measurement, and z-scores are expressed as standard deviation units. And again, without getting too much into the arithmetic or the mathematics of it, we know that roughly 95% of our cases should be between more or less than 1.96 standard deviations of the mean. We know that 99% of cases should be between plus or minus 2.58 standard deviations from the mean. And we know that almost every case, 99.999 recurring cases, should be between plus or minus 3.29 standard deviations of the mean. So if we look at standardized residuals in our analyses and we see that these are greater than 3.29, this is a big concern, especially if you've got quite a decent sample size. And we'll talk more about what constitutes a reasonable sample size later in today's session. So if we investigate our data and we find that more than 1% of our cases have residuals greater than 2.58 standard deviations above or below the mean, then it may be that there is too much error in our model for it to be generalizable. If more than 5% of cases have a standardized residual of plus or minus 1.96 standard deviations from the mean, it may be that the model is not a good approximation of the raw data. There's just too much of this leftover unexplained residual error. So we have to be quite cautious, and with decent sample sizes we can be quite bold in removing cases so that we are fulfilling the assumptions of the models. We are removing problematic outlying cases, and we are hopefully then going to be able to build a model which is more generalizable. There are certain cases that may be more or less influential than others, and this is especially important if you are using a linear regression model. We may have to make other considerations here and use other methods to identify outlying or unduly influential cases within the data set. We're not going to talk about this in great deal during this session. Subsequent sessions on linear regression will address this issue, and it is best discussed within the context of regression analyses. So just like previous studies or previous modules where you may have studied analysis of variance. When we talk more broadly about general linear models as part of the family, which includes ANOVA, but also includes other techniques such as linear regression and analysis of covariance and even multivariate analysis of variance, we still have to satisfy a number of assumptions about our model. There are some interesting papers for those of you who are particularly research methods minded by Gelman and Hill and by Field and Wilcox, which address these important assumptions. And the main considerations to make are those around additivity and linearity. And again, without getting too much into the mathematics that underlies the general linear model, part of the core assumption is that your outcome or your dependent variable should have a linear relationship with any predictors, or you could think of these as independent variables. Think for a moment about when we try to do a correlation analysis. One of the things that we should consider is there any evidence that the relationship is either linear or non-linear? Because a correlation is essentially a test of a linear relationship. And a lot of people would argue that things like correlation and ANOVA, which are typically sort of housed very, very differently in research methods teaching about relationships versus differences, a lot of people might even argue that something like a t-test or a one-way ANOVA is actually just a type of correlation where you move from one level of a variable to another and observe what happens to your outcome. Again, without getting into the mathematics of this, it's a very, very interesting consideration. And again, the take-home message at this point is that we can kind of stop thinking about tests like correlation, regression, and ANOVA as being completely different from one another or even used for very different purposes. They all kind of come under this umbrella term of being linear models. So another thing to think about is that if you have several predictors or independent variables, the combined effect of these should best be described by adding the effects together. Now, that could include an interaction term. So it doesn't mean that the factors have to be operating independently. It just means that the effects of single factors, single predictors, or indeed the interactions between multiple predictors should best be expressed by adding them together. There are ways and means that we can work around violations of this assumption. So for instance, if our variables do not appear to have a linear relationship, if they appear to be curvilinear, for instance, we can perhaps transform the data to make it better fit a linear approximation. So to give you a real-world example from my own research, often when you look at things like reaction time data or eye movements during reading, the data does not have a linear pattern, or it is perhaps somewhat curvilinear in terms of residual error. One thing you can do with this type of data is to apply what's called a log transformation, and this essentially should tighten up the residuals and make for a more linear relationship between your variables. This is quite hard to conceptualize without having a data set in front of you, or indeed to have actually performed some analysis. So in future, when you are conducting your data analysis, please carefully consider these types of assumptions, and either through visual inspection of your data or through some other quantifiable means, consider whether or not there is evidence of either a linear relationship with the outcome and your predictors. And if this is violated, explore the ways in which you can rectify this, rather than abandoning your plan to proceed with a linear model type analysis. Another assumption associated with all linear models or all tests associated with linear modelling is that the errors are independent. So for any two data observations, the residuals should be unrelated or uncorrelated. So for instance, this might be participants mean scores. So participant 1, the mean of that participant and its associated residual error from your model should be independent from the residual error associated with participant 2, with participant 3, and so on and so forth. And this is why it's not just unethical to get multiple participants to complete the same version of your test or your survey. It actually can potentially very much invalidate the statistical test that you're using to interpret your data. So yes, by essentially cheating and testing multiple participants multiple times to get your sample size, you might actually be counterproductive, and you might actually be removing any chance of finding a generalizable, reliable and robust effect. If you are conducting a regression analysis, which again is just a type of linear model, you might wish to consider additional tests to check the independence of your errors. The example would be something like a Durbin-Watson test, which is really quite niche, so we're not going to talk about it in any detail just now, but further down the line, in sessions where you're learning about regression analyses, this is something to have at the back of your mind. And certainly if, when you come to conduct your own independent research or research as part of a project team that involves linear regression, this is something you may wish to consider. Homoskedasticity. You can't imagine how many times I've been practicing that before I began this narration. It's not an easy thing to say. What it ultimately means is that at each level of your predictors, the variance associated with your residual terms should be constant, or an approximation of constancy. So if we have multiple levels of a single predictor, our model should equally predict, or predict equally well, each level of that predictor. Normally distributed errors models are strengthened when your residuals are random, when they are normally distributed, and when they have a mean close to zero. So that essentially means, again, without getting too much into the mathematics of it, that when you fit your model to the data, there are approximately equal number of cases where your model underestimates the score within the raw data, and approximately equal number of cases where the model overestimates the score. If we think of essentially trying to draw a straight line through our raw data, which would reflect the predictions of the model, what you're basically saying here is that we have about half of the cases physically above the line that was predicted, and about half of the cases that are physically below the line that you've drawn across your data set. Ultimately, this should yield differences between predicted and observed values that are close to zero, or very close to zero, when we look at them at a mean level. And the closer we can get to this, the stronger our model actually is. Okay, sample size. Now, sample size is a bit of a controversial issue, and it's one which is often misinterpreted around the concept of linear models. So historically, when you were being taught how to do things like analysis of variance or t-test, which are part of this family of linear models, you were maybe told to aim for something like 20 participants per group, or 20 participants to do each level of a repeated measure design. And there is a little bit of logic to this, and again, I don't want to get too much into the mathematics of sample sizing, but the long and the short of it is that, generally speaking, the larger the sample, the better for your power in your analysis, therefore reducing the likelihood of making errors in your interpretation, and also the likelihood that you can genuinely trust the results that you do find. We also have to be, however, practical and ethical. So we don't necessarily have the time or the physical space or the access to the population that we require. So we can't just aim for, enormous samples of 200 or 300 participants, particularly if you're collecting data face to face, or your data collection might require extensive time commitments from your participants. So we have to maybe consider determining our sample size from maybe doing a rule of thumb or a power calculation by looking at what previous studies have done. And ultimately, what should really determine how large your sample is a consideration of how many predictors or independent variables you have, how many levels each of these have, and the anticipated or the known effect size that should be yielded within your study. And again, this can be based empirically from previous studies or from a theoretical standpoint. If you're looking for a smaller effect size, or the effect size that you're anticipating is a small effect size, you typically require a larger sample to avoid one of these type 2 errors. And the more predictors that you are entering into your model, be it in an analysis of variance or in a regression, you require more observations to avoid these type 1 errors. And this is maybe a useful point to pause and just refresh yourself about what we mean when we talk about type 1 and type 2 errors. From an ethical perspective, we also have to think about if we are using participants' time fairly. So for instance, if 77 participants is going to be powerful and adequate enough as a sample for your study, don't test 777. What are you really doing with those other participants' data? And also for certain statistics, you might inadvertently force a result by throwing a tremendously large sample at it. So be pragmatic, be ethical, and try to use either an empirical or a theoretical basis for determining your sample size. It is possible to perform things like power calculations, but again, I'm not going to get into those either mathematically or even theoretically in this session, but I would be happy to discuss those with you independently. Let's talk about categorical predictors. So if we are comparing two means across two groups, essentially what we are doing is predicting an outcome, a dependent variable, based on membership of a particular group, which is essentially levels of the independent variable. And again, without being mathematical about it, what we are essentially doing is trying to fit a linear model to our observed data using one dichotomous predictor, i.e. a predictor that has two levels. So when we compare these two means, we are basically using a special case of a linear model. So going back to the point from earlier about this family affair between regression and analysis of variance, or regression and the t-test, you can hopefully see why there is actually so much underlying similarity and why these tests belong to the same families. We are essentially looking at a relationship between predictors or IVs and an outcome or a DV, regardless of whether we are using a simple linear regression or a t-test or an ANOVA. Now, one thing that you may have done before and that may not have occurred to you before is that when you're maybe coding a nominal variable into SPSS, for example, we sometimes more or less randomly assign values. So for instance, if we are coding levels of highest educational qualification achieved, we maybe code a high school level qualification as 1, a further education college as 2, undergraduate degree as 3, and a postgraduate or postdoctoral qualification as 4. Now, if all we are doing is using that data to describe the makeup of our sample, to provide frequency tables, for example, that's typically fine. Or if we are setting those up to be somehow important for determining our descriptive statistics. The problem comes is that if we use this kind of random approach to numeric categorization with a variable that is going to be entered into one of these linear models, because in that case the numbers actually take on significance. So without going into the mathematics of it in too much detail, we have to be a little bit careful as we move forward into higher level analyses when we're considering linear models, particularly those around regression and in particular multivariate regression, about the numeric values that we assign to represent our levels of predictor. I'm not going to go into it too much just now, but the long and the short of it is that a lot of people wreck their linear models by treating the coding like they're setting up a demographic variable in SPSS. If you're going to be performing these analyses on your own data, I would encourage you to read very closely around the concept of dummy variables and how these are set up, because the mathematical consequences of sort of going in willy-nilly and assigning numeric values to predictors or levels of predictors can actually totally undermine your linear model. So at this stage, try to be a little bit careful when thinking about, am I setting up this numeric variable in something like SPSS simply to allow me to describe some characteristic of my sample, or is it something that I'm going to try and factor in to a linear model? And it may be that you actually code the same variable, for instance, sex, or level of educational attainment, or participant group, or professional identity. It may be that you actually code that variable in multiple ways in your data set. But again, this is sometimes quite hard to conceptualize without having data in front of you. And I don't want to get into the mathematics of it just now, but it's something that will maybe be revisited when you look at regression analyses in particular. And again, if this is something that's going to be relevant to your own analysis, then it's something to certainly read around and to potentially discuss with a supervisor or a colleague. We are not limited, of course, to comparing two means using a linear model. We can compare multiple means. And again, this is one point where there's a little bit of a misconception, where people perceive a much larger difference between ANOVA and regression than there actually is, both theoretically and empirically. So again, one thing to always have in mind is that what most people think of as being the ANOVA is just this F statistic that is the test of the fit of the linear model. So F is not unique to ANOVA, even although that's where we sort of mostly see it. And what we're ultimately still doing is using this F value to establish whether or not our model predicts or fits our observed data well. This is really unfortunate, and to be honest, if you're going to point the finger at anyone, point the finger at previous generations of statisticians and research methodologists. There are some really quite unusual historical arguments about why people have kind of fallen into these camps of being ANOVA people or regression people, but ultimately, they're not Hatfields and McCoys. They're actually part of the same family. They've just become a little bit alienated from each other over time, but you as the future of research methodology and research in statistics and psychology, you can help to mend some of those fences. What we have in the case of an ANOVA essentially is that the model represents a series of group means, and that the F value, the F ratio, is telling us that using these group means to predict your outcome is actually better than just using the overall mean. So if we have a set of participants who maybe differ on two levels of one variable, let's say sex, and we give the participants a task to do and we establish their scores, we could get an overall mean performance of a person, a participant within that sample. So if we had 20 people who identified as males and 20 who identified as females, we could add up all 40 scores, divide by 40, and get a grand mean for that sample. Alternatively, we could establish the mean for the male identifying group and the female identifying group. We could try to build a model and we could see whether those means are a better fit to the data than simply using the grand model. What this will then tell us is whether or not the group means are significantly different from one another, or indeed that they're non-identical. And think back to when you maybe learned about analysis of variance in the past. If you have more than two group means, so for instance, if we take our example that we mentioned a moment or two ago, if we had participants who identified as female, male, but we added a group who identified as non-binary, then the statistical test wouldn't tell us which groups are different from one another. It would just simply tell us that the groups are different. We would then need to follow up with things like pairwise comparisons, t-tests, etc, etc, etc. So although the examples so far have kind of been housed around sort of ANOVA and regression, it's ultimately important to remind ourselves at this stage that ultimately we've been talking about linear models. So the F statistic that comes out when you do something like a regression, an ANOVA, an analysis of covariance, a multivariate analysis of variance, is again just measuring that ratio of the variance in your data that you have been able to explain with your model versus any remaining unexplained or unsystematic variance. And we could think about this as basically being a signal to noise ratio. So your signal is kind of the stuff that you've been able to explain, the stuff that is due to what you have manipulated, controlled for, investigated, explored, and the noise is all the other stuff, the individual differences, the error, and so on and so forth. In an experimental design, you could think of this as being the ratio of your experimental effect to individual differences. So how large is this experimental effect in relation to the individual differences? So this is why we have to have different analyses of variance depending on the design. So for instance, if we have a within or a between subjects design, because how we cope with the individual differences in those designs is different. The underlying formulae, and again, without getting into the mathematics of it, the short story is that the formulae are different. So if we were to use the inappropriate linear model for our design, we have a problem in the interpretation. And to reiterate a point from earlier on, this F ratio, this F statistic, if it's less than 1, it means that our unsystematic variance, our error, our individual differences, is greater than the systematic variance. So if we think of that as a ratio, it's saying that the largest part of the ratio is the unsystematic part, is the error. It is going to dwarf the systematic or the experimental factor in your analysis. Therefore, why f less than 1 can never be significant. An f value equal to 8 means that the systematic variance is 8 times larger than the unsystematic unexplained variation. So hence, the larger the f value, the more likely it is that we will get a significant effect, and the more likely that our systematic model is explaining a large enough proportion of the variability within the raw data. The p-value that is associated with the F statistic represents the probability of obtaining an F value of that size due to chance or due to error. So again, the smaller the p-value, the less likelihood that your F statistic is due to chance or due to error. So large F ratios generally relate to small p-values, and remember that the p-value is ultimately saying what is the chance out of 100, or the proportion out of 1, that your result is due to error or chance. So the smaller that p-value, the less likelihood that your result is a fluke or an error. Let's go back and talk a little bit more about assumptions. And just like all linear models, we assume homogeneity of variance. This goes back to instances when you've maybe been taught about things like t-test or analysis of variance. The variance in outcome remains a constant. Excuse me. The variance in outcome, your dependent variable, should remain reasonably constant at each level of the predictor. Homogeneity, it means the same variance at each levels. Now, where we have a big problem here is that if we're dealing with unequal group sizes, if we violate the assumption of homogeneity of variance with unequal group sizes, this has very serious consequences for our linear model. And in the past, with things like t-test or other forms of linear model, we can use a Levene's test to explore this assumption. And what we look for in a Levene's test is a non-significant result, a p-value that is greater than our threshold of 0.05. What this is telling us is that we could not reject the null hypothesis that variance is equal. So by default, by null, we are saying that the variance is equal across our levels. If we find a non-significant result, we cannot reject that assumption of equality. So we proceed, assuming homogeneity of variance. If the Levene's test is significant, we don't panic. We don't abandon our linear model. What we do is we potentially use a corrected version of the F statistic. Now, this might be known as the Brown-Forsyth F value, or alternatively a Welch's F. And during this presentation, we're not going to cover these in a lot of detail. However, if you are very interested in these, or indeed when you are performing your own statistical analysis and you have concerns about the homogeneity of variance, then revisit these concepts of Brown-Forsyth F or Welch's F. One myth that many of you will have experienced in the past is that it's fine, just go ahead with the ANOVA. It's robust enough to handle violations of the assumptions, so unequal group sizes, missing cells, heterogeneity of variance. Field and Wilcox, for those of you who are really interested in this kind of thing, have provided a nice review of why that statement is misleading in many cases. So there's lots of ways to get around this. So for instance, if you just by default use this Welch's F statistic, then you don't really even need to worry about homogeneity of variance. There's also a concept called bootstrapping your parameter estimates, and when you're using techniques like SPSS, you might actually see the opportunity to bootstrap your data. Now, this doesn't influence your F statistic, but what it can do is tighten up your model parameters. And again, we're not going to talk about bootstrapping in great detail in this session. However, when you're reading papers that have used linear modelling, you might find them talking about bootstrapping. And this is particularly the case when you look at things like correlations with massive samples, regressions with lots and lots of data observations, or indeed ANOVA, ANCOVA, or MANOVA. And as a fallback, we have the Kruskal-Wallis test as an alternative to our analysis. It's a non-parametric linear model to all intents and purposes.